Any big news for this weekend? Any big plans? You have a soccer game this afternoon, is that right? At 4? So it's out on the field. Any other things going on this weekend? No? What's that? Vacation, where are you headed? Oh, okay. Good. Hopefully it's a good weekend. I don't know what the weather's like this weekend. Is it good? Good. Good. Anything else this weekend? We have a pretty normal weekend. We have a stock up trip tomorrow for our groceries. Like once a month we go and we buy like $400 worth of groceries. So like our cupboard is completely bare. We have no food. We've been sort of scraping by all week. So we're gonna do that. That's exciting, right? I don't know. We'll probably go for a bike ride Saturday morning. Hopefully we get to go to the pool. The pool's still open till. Well, the pool here, is like open almost year round. So, and y'all have access to the pool too. All right. You have any questions about what's coming up? I know there's an exam on Friday. Is that right? Yeah. That exam will likely just cover chapters 1 and 2. We might get a little bit into chapter 3, just a tiny little bit, just to sort of throw some easy stuff into the exam to dilute it a little bit, but probably just chapters 1 and 2. Okay? And then the next one will probably cover chapters 3 and 4. Although, actually, this exam, the time is a little short between the first day and the exam, a short number of class days. In later exams, we'll have a longer number of class days, so we'll cover more material. All right, let's work through some problems. All right. I would be definitely, you've already worked through those chapter 1 homework. I would also begin working through the chapter 2 if you haven't yet. Get a start on it today. Just half hour a day. It's good. Let's do this quick test. I've actually changed it a little bit because this is really a two-dimensional problem, and we haven't really had everything that we need to work this. So I've just changed it a little bit into a one-dimensional problem where I took out the first part of this function. Remember I talked about I and J notation, how I refers to which axis? The x-axis, and J refers to the y-axis. They're just what we call unit vectors. They just denote what direction they're in. So here we have a function 5.6t minus 4.9t squared. And the first thing I want you to do is just give functions for the particle's velocity and for the particle's acceleration. So I know that the position function, which in this case is x, because I've taken out the y, or excuse me, is y, is equal to 5.6t minus 4.9t squared. And now I want to know what are the functions for the velocity and the acceleration. Just take a minute and find the functions for the velocity and the acceleration. What are you going to do to find the velocity function here? Just take the first derivative, right. So just take the first derivative of that function for y, and then you'll find the function for the velocity. All right, so I'm going to just write it up here. What's going to be my first term? Just 5.6, right? And then my next term, right, I take the 2, I multiply it by 4.9, that's minus 9.8 times t to the 2, what is it? Just t, right, t to the 2 minus 1. So my velocity function looks like this, 5.6 minus 9.8t. Let me remind you of our equation that we derived last time for the velocity. The velocity is equal to v naught plus a times t. You see how those two functions look a lot the same, right? That's because this represents our initial condition, our v naught, and our acceleration here, minus 9.8, is equal to a. Right, this is a free fall problem, which we'll get into today. Now, what about our acceleration function? If my velocity is 5.6 minus 9.8t, what is going to be my function for the acceleration? Just negative 9.8. I just take the derivative of this. This doesn't change, so the derivative of that is 0. The derivative of any constant is 0 because they're unchanging. And then this is just going to be negative 9.8. So my acceleration function then
is just equal to negative 9.8. And that's going to be in meters per second squared. All right. Now, we've already sort of answered this question, but what is the magnitude and the direction of the particle's initial velocity? It's going to be 5.6. That's right. Remember, this is given in this function. It's the 5.6. What's the direction of the initial velocity? What's that? Up or to the right, but in this case, it's going to be up. So because this was originally a 2D problem, this was a projectile motion problem, we're just sort of editing it. So we're giving now our function for y. So our initial velocity is positive, which in this case, because it's in the y direction, is going to be up. So it's 5.6 meters per second, and it's in the upward direction. I want you to sketch the velocity versus time graph for the y component of the velocity. I want to see a sketch of the velocity in the y direction versus time. What does the velocity in the y direction versus time look like for this graph? What happens to the velocity versus time for this function? The initial velocity is positive or negative? The initial velocity is positive, so I'm going to start with my first point right up here at positive 5.6, and then where's it going to go from there? Is it going to go up or down? What should the slope of this graph be equal to? This The slope of this graph should be negative 9.8, right? Because our v versus t graph has a slope that's equal to the acceleration, and in this case, our acceleration is minus 9.8. By the way, guys, I posted a note on the forum, you'll get it during class today, about the value for g. In the past, like if you look at old exams and old homework problems, you'll see that I've used a value for g equal to 9.8, but I find that it's easier just to use 10. It just makes the math a lot easier. So on the tests and just sort of as you're practicing, just use a value for g equal to 10. But that might mean that on some of the old exams that you get an answer that's slightly different. Just be aware of that. But I think it'll be easier for you just to use a value for g of equal to 10. All right, so here my slope should be negative or positive? Negative, right. So my line is going to look like this. And then we'll see, actually, that it will continue on like that. So if I were to draw this, I would have a positive velocity initially and a negative velocity afterwards. All right, it's going to look something like this. This is the scenario that we're dealing with. We take something, we throw it up, and it comes back down again. All right, at t equals 0, it's here. It travels up, 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 and then it comes down, down, down. All right, where is the velocity positive? In the first or second half? In the first half. It's going up, and then it comes down. And that's represented in this graph, where as I throw it up to the top of the trajectory, it comes to this point. What happens at the top of the trajectory to the object, according to this graph? It stops. Right, watch it. It's going to stop. All right. Anyway, it stops when it gets to the top, and then it turns around and starts going in the negative direction. Okay, so if I were to think about this, let's write this. If I were to think about this, I take an object and I throw it up, 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 and down, 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 down. All right, at the top, I have a velocity equal to 0. I have positive velocity here. I have negative velocity on this side. We're going to do some free fall problems like this, and it'll be very, very important that you master them because when we move into 2D motion for projectile motion, this is going to be pretty crucial that you get this sort of idea in one dimension. All right. So we'll work some more problems like that. By the way, you're very likely to have a problem like this where I give you functions for the position. You have to take derivatives to find the velocity and acceleration functions, and then also maybe graphing some things like this, telling me particular values for velocity or acceleration at particular times. So you will have a problem similar to this where I give you functions and ask you questions about the motion, ask you to graph things, ask you to calculate things. Okay, Okay, now let's look at parts D and E, and this is sort of getting into these free fall problems. I want to know what is the total time that the particle is in motion, and then I also want to know what is the maximum vertical range of the particle. Couple things you want to note here is that the velocity here at the top is equal to 0. I'm going to write my two equations. I have V equals V naught plus AT, and then I also have Y equals V naught T plus 1/2 A times T squared. What you want to do here, we'll work another problem similar to this in just a minute, but what you want to do is you want to first find the time that the object is in the air. Actually, you're going to find half the time that the object is in the air, and then you'll take that time and you'll use that to find the maximum range, or how high it goes. All right, which of these formulae could I use to find the time that the object is in the air? The y one? Let's see, I could, except I don't know what y is. So I have two unknowns. I don't know what y is, and I also don't know what t is. Now I know what a is, right? Because I got that from that derivative. And I also know what v naught is, because that was in that function as well, that negative 5.6 or whatever it was, I think. All right, so you're going to run into a problem here because you have two unknowns, and you can't solve that with two unknowns. Well, let's look at this. Do I know v? Do I? What is v? It's 0. Very good. Uh, v is 0 here, but a particular velocity, the velocity at the top of the trajectory. V naught, I know what that is, right? What was that? 5.6. Very good. And I know what a is. So I'm going to take this top equation. I'm going to rewrite it a little bit. I'll say v top equals v naught plus a. I'm going to call this t-top because that is the instant in time when it reaches the top of the trajectory. So then I can put in some values here. And I can solve this for t-top. That's just going to be 5.6 divided by 9.8. I get 0.6 seconds. That's what y'all got? 0.6? All right. Okay, so for part D, it asks, what is the total time that the particle is in motion? What's my answer to that part? 1.2, that's right, Beans. So 1.2 seconds because the object, where's my marker? The object goes up, and after 0.6 seconds, it reaches the top. And then how long does it take to come back down again? 0.6 seconds. It's symmetrical. Anytime you have motion like this, the times are symmetrical. If they're covering the same amount of distance, the amount of time to go up is the same amount as the amount of time to come down. So the amount of time to go up equals the amount of time to come down. So the answer to part B or whatever that was is that the total time is equal to 1.2 seconds. Right, now I want to know what is the vertical range of the particle. And Ainsley, which am I going to use for that? Right, I use the y one. Very good. So I use that equation. Now it's pretty simple. I'm just plugging in numbers to find what is the y range. I say y is equal to 5.6 times t. Oh, shoot. Which time do I use? Now I have two times. I have the 0.6 and I have the 1.2. I'm going to use the 0.6. Listen, guys, these are just functions, and they tell the positions at particular times. So if I want to know the position of an object at any time, I can just plug in that time, and it'll tell me what is that position. And so I want to know the position at a particular instant, at a particular point, and that point is up here. And I know the time at that point is 0.6 seconds, so I just put in 0.6 seconds. Minus 9.8, or minus 1/2 a times 0.6 squared. That's using this function up here. And I get get 1.6 meters. So that is the maximum Y height. Somebody told me what instead, if I accidentally put in the other time that I had, let's say that instead I put 1.2 seconds there, what would I find would be the position at 1.2 seconds? It's going to be 0, right? So if I put in 1.2, it will turn out that this term will equal this negative term, and it'll be 0. That's right, because now if I'm starting at an initial position equal to 0, which is right here, and it leaves my hand, after 1.2 seconds, it returns back to that original position, which would be at 0. All right? Likewise, what if I said, what is the position, say, at, I don't know, 1.8 seconds? What type of value would I get? Would I get 0, a positive value, or a negative value? Or let me show you. Well, let's say it goes up and then it goes down here. I'm going to get a negative value, right? Because it goes up and then it passes the 0 point and then it keeps on going down. So my position then will be a negative value. We're going to see a problem like that in just a few minutes today. All right. So 1.6. This is a sample of a problem. You'll have some other kinematics problems like will work in the homework or in the supplemental problems that I sent out, but you'll also have a problem like this where I give you functions and I ask you to do certain things with them and respond about what is the object doing, what's the motion like. Y'all could do that for me? First thing would just be doing the derivatives. Make sure you got those because that'll be some points, definitely. And then plotting graphs and talking about sort of the position and the velocity. All right. Let's see. Let's watch this little clip. This back. Sorry, YouTube won't let me post videos of videos, like recordings of other videos for copyright or whatever. So we're not doing the Mini Cooper. We're actually doing the drag race. All right. So I have this car. I know some information about it because it's given here. This Lamborghini. I know 3 things about it. I know that in a time of 10.8 seconds, that it travels a distance equal to a quarter mile. And I know that its top speed at the very end there was 132.3 miles per hour. So the final speed was 132.3 miles per hour. Let's just first off make these conversions because we want everything in SI units. Quarter mile, I know that in 1 mile there are 1609 meters. And if I do a quarter of that, that's like, what, 403? No, 402.3. 402.25. So 402.3, I'll call it. All right, 402 meters. And I want to convert this to SI units as well. Make sure that you're up on this, okay? You'll have some explicit problems, multiple choice probably, where you have to convert units. But also, all semester, you might have to convert units on various problems. Not very many, but occasionally you will. So you should be pretty good at it by now. I know that in 1 mile, there are 1609 meters. And in 1 hour, there are 3600 seconds. All right, nothing squared, so I just keep everything like it is. And I find that that's equal to 59.14 meters per second. All right. Now I want to know a couple of things about it. I want to know, first of all, what is the acceleration? What is the acceleration of this car? How would I do that? I'm going to write my equations over here. I recommend that when you get your test next Friday that you just sort of scratch these out on the top of your test. Just so you have them in front of you. It's nice to see them. these are my two kinematics equations. I also haven't written one quantity here that I know, but I haven't written what is that quantity about these cars. I know what V naught is. What is it? What is V naught? Somebody? It's going to be 0. So the initial speed here is 0. So I'm going to simplify these equations a bit. I can just scratch out this because that goes to 0. And since this is 0, V naught, if I multiply it times t, the whole term goes to 0. So I'm just left with V equal AT and x equals 1/2 A times t squared. So I'm going to use, I could use either actually. I'm going to use this one to find out what the acceleration is. I'll show you why in just a second. You could use either, but you'll actually get different values. But I'm going to use this one. I'm going to say that V is equal to the acceleration times the time. That is at 59.14 meters per second is equal to the acceleration times 10.8 seconds. And then I solve that for the acceleration, and I find that that acceleration is 5.48 meters per second squared. I want you to go and plot what is the v versus t graph for this motion. What does it look like? Should be pretty simple. What is the v versus t graph for that motion as well? You'll definitely have some plotting problems where I give you a scenario and then I ask you to plot what that motion should look like. So used to that. And then when you do that, go ahead, if you've already plotted it, go ahead and calculate now what should the distance be. So plot out v versus t, and now that you know the acceleration, act like you don't know the distance. And we know it's a quarter mile, but act like you don't know the distance. I want you to calculate what that distance should be. Take a minute to do so. That's right. Very good. Awesome. Go ahead and calculate the distance that it travels. Might holler out that distance when they get it. Not everybody at once. But I have the distance. Kylie, you have it? It's Kylie, right? Yeah, do you have it? No, okay. What you got, Ainsley? Yeah. Do I have it? The distance? What you got, Brandon? Yeah, 320. That's kind of funky, isn't it? Because we know for sure that this thing has traveled a quarter mile. It's a quarter mile track. Like that's what they do, right, when they have these races. So this is definitely a quarter mile track. Oh, and what should the V versus T graph look like, by the way? It's been pretty straightforward, right? What's it gonna look like? It's a straight line. It starts at the origin. It goes up like that. It has a positive acceleration, so a positive slope. All right, and we also know a couple things about this, that the velocity here is 132, or let's see, we found it to be 59. And we also know that the velocity here is 0. Those 2 points are fixed. And we think we know the acceleration, that it's 5.48. But if we calculate the position at that time, x equals 1/2 at squared, I get x equals 1/2 times a, which I found to be 5.48 meters per second squared. times t, see what was t, 10.8 seconds squared. That gives me 100, or no, excuse me, as y'all said, 320 meters, or 319.6. I'll just write 320. All right, which is less than the value that we calculate for a quarter mile, which is approximately 400 meters. So what is going on there? Why do we get a value for our distance here less than the actual value, assuming this acceleration that I found to be 5.48? It's not a constant acceleration. So our assumption over here for our v is not correct. So I'm going to give you a couple other options. I want you to think about what it could be. Another option is that our velocity could start here and it could go up like this. Or perhaps another option, let's see, let's put it in black, is that it starts here and it goes like this. See, I'll call this A, B, and C. Which is it? Which is the correct way of doing this? Is it going to be A, B, or C that would actually represent what the cars are physically doing? Okay, I have A and C, A and C. Now remember, for position, velocity versus time graphs, we can get two pieces of information from them. The derivative of a velocity versus time function is the acceleration, right? That's also the slope. The integral of the velocity function is equal to what? The total distance. The integral is just a fancy way of saying the what. The right, no, an integral, when you take the integral of a function, you're finding the what under the function. The area, right. We'll see that in the lab soon. Um, so if I take the integral of this function, a, b, or c, that'll give me the total distance traveled. So which of these will give us the appropriate total distance traveled? I know that if I take the integral of b, that's going to give me 320 meters. So which function will describe the actual motion of the cars to give me an integral that's equal to the actual distance, which is 400 meters? A. Right, so my cars are actually following the path of A, and if I integrate that function, that's when I get the 400 meters. That sort of makes sense if you think about it, because if I look at this function as I've drawn it, these my cars are traveling like this. Initially, they start out with a big or small acceleration, a big acceleration. And then as they get going faster, they stop accelerating so quickly. Because the faster you go, the harder it's going to be to move that big old car. It just takes a lot more energy the faster you go. It's a lot easier to accelerate at low speeds than it is at higher speeds. We'll talk about that more when we get into chapter 5. Okay? Let's do some clicker questions, sort of explore some of these ideas. I forget where we left off last time. Somebody remind me? Do you know, Lindsay, where we left off? Do you have it written down? Who has it written down? Claire, you have it written where we left? 2.8? Right here? This one? Okay. Oh, shoot. I have to get my clicker thing back. Uh, Sorry about that. By the way, did y'all see that picture of me and my son on that kayak in the kayak? Did y'all get the little question? How fast could a kayak go roughly? 1, 10, or 100, or 1,000? How fast? I'm sorry, who said that? Yeah, about 1 meter per second. Just to give you an idea, 1 meter per second is equivalent to about 2 or 3 miles an hour. So, not real fast. Maybe if you're a really good kayaker, you can go faster than that. But, so if we spend about 1 meter per second, what did I say, about 10 or 15 minutes to go across? So how far is that across the little inlet we were in? Right, about 900 meters. So like 10 minutes would be 600, 15 minutes would be 900, so somewhere between 600 and 900 meters. All right, that was just sort of for you to think about. And it was a lot of fun. Like, have y'all ever been to Page, Arizona? It's awesome place. Huge lake. The it's the Colorado River that's been dammed up. That lake has more coastline than the Pacific coast of the United States. It's really amazing because there are all these little inlets that go into these like canyons, and there's caves and all sorts of cool stuff. It's a desert, right? And then they flooded it. But all right, let's see. Velocity of the car is non-zero. Can the acceleration of the car be zero? If you're watching earlier, you should know this. All right, I'll stop at 20. A is the right answer. Uh, a car with a non-zero velocity but zero acceleration is just a car traveling at a certain speed, right? It's neither speeding up or slowing down. It's just traveling at a constant velocity. So it has a zero acceleration. And throwing a ball straight up. Oh, let's go back and think about this for a second. Can a car with a zero velocity have zero acceleration? I've already said that a car with zero acceleration can have non-zero velocity, but is the opposite true? Can a car with zero velocity have non-zero acceleration? Just think about that for a minute. Well, let's look at this question. When throwing a ball straight up, which of the following is true about its velocity and its acceleration at the highest point in its path? Velocity equals zero and acceleration equals zero, or some combination of those two where they're not equal. All right, I'll stop at 35. 35. All right, let's think about this. So if I have, where's my marker? I'll use this one. If I have this thing and I throw it up and it comes back down, we know at the top that the velocity is what? All right, we've already talked about that. What would happen if you threw it up and the acceleration went to zero at the top? Remember the acceleration, thank you, Beans. The acceleration tells you how the velocity changes. And so many of you, 15 of you, say that when you get up to the top, that the acceleration goes to zero. That means that what happens to the velocity? It stops doing what if the acceleration? It stops changing, right? So imagine if my acceleration is zero at the top, what happens to my marker? You're gonna throw it up and it's gonna go, whoa. Okay, if your acceleration goes to zero, that means the velocity stops changing, right? In which case it would just stay here. But if the acceleration is non-zero, that means it's going to turn around and come back down, which is what it really does. We know that the acceleration is always equal to that minus 10 meters per second squared. We'll get into this in chapter 4. It has to do with the gravitational force, that there's always a force acting upon it, and that force causes that acceleration to always occur. But for now, we just know that it has an acceleration that's equal to negative 10. So what's the answer here then? C is the right answer. Good job, the 8 of you. A is sort of the most common answer that people put. All right. Alice and Bill are top of a building. Alice throws her ball downward. Bill simply drops his ball. Which ball has the greater acceleration just after release? Just after the ball leaves their hand. Which has the larger acceleration? Awesome. Ask your neighbor if you're not sure, okay? A few of you have the wrong answer. I'm going to stop at 40. I'll just give you till 43. Okay, C is the right answer. Um, Now Alice is throwing her ball down. So we know that its initial velocity is going to be bigger, smaller, or the same as Bill's ball. It's going to be bigger because she's throwing it. She's giving it this initial velocity. So in that function, v equals v naught plus at, we know that Alice's ball will have a bigger v naught. But they both still have the same acceleration. Because anytime you have something that's falling within the Earth's field, within the Earth, around the Earth, it has an acceleration equal to minus 10. So it's always going to be minus 10. So both of these are going to have the same acceleration. Which one has the greater velocity when they hit the ground? Think about this function, okay? V equals V naught plus AT. Which of those will have the greater velocity when it hits the ground? Alice's or Bill's? Alice, right? Because she throws it. She gives it an initial oomph right here. This term is going to be the same for both of them, but she'll give it an initial push, which gives it that greater initial velocity, giving it a bigger velocity at the ground. You throw a ball upward with a speed of 10 meters per second. You assume there's no air resistance. What's its speed when it returns to you? More than 10, 10, less than 10, or 0, or just not enough information. Right, awesome. Just a few more seconds. I'll stop at 35. Great. It's going to be equal to 10 meters per second. It'll have the same speed that it left your hand with. Knock, knock. Interrupting pirate. Arg! I've heard that one, haven't you? Have you heard it? It's a good one, though, I think. Okay, you drop a rock off a bridge. When the rock is falling 4 meters, you drop a second rock. As the two rocks continue to fall, what happens to their velocities? All right, y'all got this down. I'm going to stop at 40. All right, good. A is the right answer here. Uh, D isn't the right answer because the velocities are going to be increasing. They're going to both be increasing at the same rate. Now, which one will have the greater velocity at a particular instant in time? The one you drop first or the one you dropped last? The one you drop first, because when you drop the second rock, that first one is already going. So it's like it has that bigger initial velocity. It's kind of like the rock that Alice threw down, right, with Bill. And so it will have a bigger velocity, but they're going to both increase at the same rate. Give me just a second. I want to check something, see if I put a question here. Okay, looks like I did not. Okay. The graph of position versus time is given here. What can you say about the velocity of the car over time? We looked at these last time. And you'll have some questions where I ask you to either sketch graphs or describe graphs of motion. What can you say about the velocity of this car over time? Is it speeding up all the time, slowing down all the time, moving at constant velocity? Sometimes it speeds up, sometimes it slows down, or you're just not really sure. Let's stop at 45, 45. Oh, all over the board. Okay, no, let's just start over. All right, look, guys. When I'm asking about the velocity of a position versus time graph, a position versus time graph gives me the what? Or it gives me the position, but if I find the slope of it, what does the slope of this graph tell you? The velocity. So when I ask you about the velocity of an x versus t graph, the slope describes the velocity. We did do this, right? We did this. We looked at all these graphs. Is that right? Yeah. Okay. So here, what is happening to the slope of this graph? Is it increasing or decreasing? Like here it's steep, here it's shallow. And once you answer that question, that'll tell you what the velocity is doing. Whatever the slope is doing, whether it's increasing, decreasing, positive, or negative, that's what the velocity is doing. So let's try this again. I'm going to stop at 1 minute. 1 minute. Doug. Okay, look, the slope is big initially. The slope is really big there. It gets smaller and it gets smaller. So that means the velocity is doing what? It's what? Is slowing down. So this thing is slowing down. So B is the right answer. It's definitely not speeding up. Now the position is increasing, right? It is going a further distance, but as it's going that further distance, it's slowing down. That would be like the first part of this. If I throw this up, when it gets up to the top, that would describe that motion because as it's going up, it's slowing down and it's also traveling in the positive direction with a positive velocity. So this object has a positive velocity. It's also traveling in the positive direction because x is increasing. Let's see, we'll have plenty of these. Don't worry, you'll get it for the end. There's the slope changing. Consider the line A. How does the speed change with time for line A? Now this is a v versus t graph, the velocity versus time graph. And I want to know how is the speed change with time for that graph? Does it decrease, increase, stay constant, increase, then decrease, or decrease, then increase? Looking at only this line right here, line A. I'm going to stop at 55, 55. Okay, that's great. B is the right answer. Simple, right? It should be simple. It's not a trick question. Here, V is some value, and then it increases to a higher value for V. So V is increasing. All right, how about for part, the line B, that is this line right here, what is happening to the velocity? Think about what the line is representing, and think about the values in particular for what that line represents. What is happening to the, or not, what happens to the speed? How does the speed change with time for line B? How does the speed change? Listen, folks, almost everybody has A for this answer. I'm going to tell you right now, A is not the answer. So rethink it, all right? I know that A seems like the obvious answer, but that's not the answer to this question. Okay, and now everybody's just guessing. And a lot of you are still holding on to A, right? A is not the answer. Think about what happens here. Starts out with a certain velocity. It's either positive or negative. Let's see, this is the origin right here, and it follows this line in that direction. So what is happening to that velocity, or the speed rather? What happens to the speed of that object? . All right, I'm going to stop at 135, 135. Okay, E is the right answer. Look, let's just give it some numbers. Let's say that this is 2 meters per second, this is 0, and then this is -2. So it starts out with 2 meters per second, its speed slows down, it decreases, and then it starts increasing again. It's the same as this, right? It goes up, it goes to 0, and then it comes back down again. Also notice that it's positive here, and it's negative here. So it's going up, then down. Right? This graph is this motion, coming up and then coming back down again. Also notice that the slope is always constant, that the slope is always minus 9.8. So on this graph, where is the top of the trajectory represented? On this graph right here. Where about? Right here on the axis. And notice that the slope doesn't go to 0 here, so the acceleration is still that -10. This graph represents this motion, uh, and it always has a slope equal to -10. Okay, well this should be easy. I just gave you the answer. Let your 1, 2, 3, 4 be A, B, C, D for your clickers, please. And that says assume, I think it says assume no air resistance. Is that right? At the bottom? That's right. I'll stop at 38, 38. D is the right answer, just like I showed before. How about you drop a very bouncy rubber ball? It falls and then it hits the floor and bounces right back up to you. Which of the following represents the V versus T? So I have a ball, I drop it to the floor, it's really bouncy, so it comes right back up. Which of these represent that motion? Think about what are the signs of the velocities at particular times and what the speed is doing. Is the speed increasing or decreasing after I drop it, after it bounces, and when it comes back up to my hand? What happens to the speed and the sign of those velocities? You're going to do a whole lab on this where you bounce balls. Ask your neighbor, folks. Turn around and ask your neighbor and say, hey, what'd you put? Say that, hey. Or just tell your neighbor. Turn around and tell them, I put E. You're not going to do it? Claire, will you tell Heather what you put? Janae, tell Taylor what you put. James, tell James, right? No, Derek. Zach, tell Derek what you put. E? E? All right. Just a few more seconds. I'll stop at 1:30. All right. D is the right answer. Notice when I drop a ball, it initially has a negative velocity. So my velocity is on the negative axis. So I have a negative velocity here. That velocity or that speed is increasing or decreasing as I drop it and it goes towards the floor. It's speeding up, right? So it's speeding up in the negative direction. And then when it bounces, a sort of funny thing happens. You have this discontinuity where it changes direction immediately. So it goes from having, say, -5 meters per second to +5 meters per second. It's kind of cool actually. In the lab, you'll bounce some basketballs and you'll actually graph this motion. It's kind of neat to see that it changes immediately in an instant the direction of its motion. And then this is at the bounce, so the bounce occurs right here, and then it slows down as it comes back up to your hand. Notice the slope of these lines are always what? They're always negative. The slope of these lines are always negative. and they represent the acceleration due to gravity, which is, you know, -10. See, I think we have one more. No, that's the last one. How much time we have left? Have enough time to do a problem? Sure, is that what you said? No, I don't think we do. But listen, y'all have a great weekend. I'll see you on Monday. Um, we're gonna have all of chapter 1 and 2 on the test. We're on Monday. We're gonna spend most of that time working problems, kinematics problems, either homework or supplemental problems, or we still have some in the notes. And we will might move on to chapter 3, just the very first part of chapter 3 with vectors, not numerical, just doing sort of basic vector stuff.